Say we start with the circular one, a very simple turbulent problem that say we have a internal flow in this case. So say I give you some different thing that we have a situation where say water is flowing through say typical dimension of our uh, tube or household pipe is say 1.25 inch diameter pipe.
Sir, are you presenting something?
Oh, okay, yeah. So we have a tube through which water is flowing, say at a certain temperature and pressure, where the diameter is 1.25 inch. The temperature in which the water flows is say 55 degrees centigrade. There is a source of heat, okay, and this water goes out of the tube say at 200 degree centigrade. Consider the inner surface is the smooth, okay, there is no roughness. So in this case, the question is what is the surface temperature of the tube at the exit? That we solved kind of a problem in the last class as well. So we have a continuous source of heat, okay. So let's convert this thing. So we have 350 watt. So this is coming in, or it is there on the surface. This is the fluid is water. So the question is, what is the surface temperature and say the length of this tube that is required to have this outlet condition, that it would enter at 55 degrees centigrade and will go out at 200 degrees centigrade, where we have constant surface heat flux condition, which is 350 watt in other way, or in a straightforward manner, if I say that it is 350 watt constant surface heat flux. The length is unknown. We have to calculate the length as well as the surface temperature at x is equals to L, if we consider this direction as x. So how do we solve this? So the properties, take the usual water property. At say here we have average temperature, of the bulk temperature, or the film temperature, whatever you call, that is directly given. I'm giving you that instead of looking at the table. So the bulk temperature would be, so the film temperature would be 255 divided by 2. So in that centigrade, say consider, assume this rough values of any say considering any steam table and all this parameter, that we have Prandtl number is 3.368 or 3.37, you can consider. CP I give you so that let you convert. So understand
units. So I want you to convert these units. Sorry, BTU per LPM. Pound mass. BTU per pound mass, and say I give you the value of nu as 0.57 into 10 to the power minus 5 meters. Here it is feet square per second. 10 square per second. Thermal conductivity value I give you in terms of 0.374 BTU per feet degree Fahrenheit instead of watt per meter Kelvin. And say I give you everything in this format so that calculation of dimension this parameter becomes easier. So the density in this temperature, that is 255 by 2 in this degree centigrade. Okay, so for the sake of simplicity, you consider this in fact everything in SI, FPS. So 55 degree centigrade, 200 degree 55 degree Fahrenheit, 200 degree Fahrenheit, and here you consider that as 350 BTU per hour per feet. So I gave you everything in FPS, which is very unconventional, but this way you should be able to calculate or convert, or just Google it and convert it at what would be in SI unit. If you want to convert this to SI unit, or throughout you can carry out with this FPS unit and report the value until and unless I ask that whether the length in meter or say the temperature in degree centigrade. These two questions. So say you calculate in terms of feet and degree Fahrenheit. So okay, so those who are confused, let me rephrase once again the problem, that we have 1.25 inch diameter pipe in which water is flowing. The inlet temperature is 55 degree Fahrenheit. Outlet temperature is 200 degree Fahrenheit. There is a constant surface heat flux condition which is 350 BTU per hour per feet. The question is, what is the surface temperature at the exit and what is the length of the tube that would be required in order to heat this water from 55 to 200 degree Fahrenheit. The properties of water at film temperature is given like this. The CPU is 1 BTU per pound mass per degree Fahrenheit. Prandtl number is 3.368. Nu is 0.57 into 10 to the power minus 5 feet square per second. And you have rho. Rho value is say 62 pound mass per feet cube. So what are these values? And how do we calculate?
Sir, we need velocity also, right?
The velocity, obviously. So the velocity is 4 pound mass per second. Absolutely.
So how do we do this? Now at the beginning, I gave you the hint that we are solving a problem related to turbulent or say internal turbulent flow, which means even if I do not tell you to calculate the Reynolds number as per Ayush's argument, you must calculate what is the Reynolds number, because then you can determine or define whether it is a laminar or turbulent flow. Because say you remember the formula or apply, because eventually you have to find out what is the Nusselt number. And if you remember the Nusselt number relation for laminar flow, and if you state that the flow, I am assuming it's the laminar flow, it doesn't work that way.
So what is that unit of velocity? Like I'm confused. Hello?
Yes.
Hello?
Yeah. Yes, Ramon, can you hear me? Or yeah,
Yes, sir.
am I audible?
Yes, sir. So what is that
Okay, yeah.
unit of velocity? I'm not be able to get it. Like what is that?
So in FPS, it is pound mass per second.
Pound mass per second. Okay, sir.
Right. So what is the equivalence in SI? Then you can quickly relate how to calculate what is the velocity. The velocity means I mentioned here, it's not velocity, it's the flow. It's my misinformation. It is not the velocity, it is the flow rate. It is flowing at 4 pound mass per second. So you have to deduce what is the velocity or superficial velocity. So pound mass per second has the equivalence in SI is the kg per second. So from there, you have to find out what is feet per second. And then you can use it in the Reynolds number calculation. So what is the Reynolds number? Has anyone calculated?
11,000.
11,000. Let me write it, 11,000. So I think still there is wrong calculation. It should be in the order of 10 to the power 5. I mean 1 into 10 to the power 5 above this value. So what is the velocity you calculated, Soham?
So 0.61 or 0.62 something.
What you again without unit? How can you tell that number?
Yes,
Is the unit?
centimeter per second, I think. No, sorry, feet per second.
Feet per second. No, that is the
Sir,
wrong
I am
value.
getting 7.57.
7 point. Absolutely. So that
Sir,
is
Reynolds number is 135.11 into 10 power 3.
just let me write 130.
135.11 into 10 power 3.
3. Absolutely. So yeah, in the order of 1.35 into 10 to the power 5. Yeah, this is fine. It should be in such a order. Yes, and someone told me that the velocity is in the order of 7.5 feet per second, right? The velocity.
Yes, sir. I'm getting 7.22 something.
Yeah. So in the numerically closer to 7 feet per second. And then you definitely get this Reynolds number, which is in the order of 1.1 into 10 to the power 5, which is much greater than the fully developed turbulent flow Reynolds number in internal flow, or completely turbulent value. So which equation we would use typically in order to find out the Nusselt number, because that is what is important to calculate the surface temperature.
So that Nusselt number is equal to 0.023 into Reynolds number to the power 0.8 into Prandtl number to the power n. That equation.
N, and N is equals to, in this case?
It will be 0.4 for heating.
And this equation you can, in short, you can, I mean, call it by name, is the Dietz-Coulter equation. So what is the value of H? Step by step, if we go. What is the value of H? Has anybody calculated? So before that, we have a step which is Nusselt number. So Nusselt number is how much by that relation that you mentioned?
So Nusselt number is coming as 475.27.
Okay, fine. So in this order, it is fine. and then the value of H.
So it is 1666.53 BTU per feet square degree Fahrenheit.
Once again, let me write it.
It is 1666.53.
1666.
Yes, sir.
Okay, fine. So yeah, okay. And this has a unit of BTU per
BTU per feet square degree Fahrenheit.
BTU per hour. And then how do we calculate the surface temperature?
So we will use surface heat flux is equal to H into Ts minus T mean and at T mean at exit. So from that we will get Ts at exit.
Right. So this surface temperature at the exit. Just like we have solved in the last class.
So how the value of H is calculated? How the value of H is calculated here?
You know now the Nusselt number,
Yes, sir.
H d by K.
Okay, sir. I was using HL by K. Sorry, sir.
Yeah, I mean, fine. I mean, L is the characteristic length or the D is the characteristic length. For the internal flow, it is the diameter.
Yes, sir. I was using the length of that pipe.
So Tanmay, what is the temperature that you are getting?
Sir, I'm calculating.
Vaishnavi, are you calculating?
Yes, sir.
Did you calculate the length by now? The length required.
Sir, can we say that the length is 10 times diameter?
10 times diameter, and why so? I mean, would that be sufficient to achieve the desired outlet temperature? Ten times is the requirement for having it say fully developed.
Because sir, in calculation of surface temperature at exit, there is a term of length. So I'm not getting how we calculate the length.
In this equation, why do you need length?
For calculating surface heat flux, we know Q, so
Uh,
Q divided by surface area. The surface area will be pi d into L.
So exactly. So that is why I asked that. Did you calculate the L by now? Because that is, although I asked it later that what is the length required, it basically comes before calculating this TA that is required. So how do you calculate the length that is required?
So through MCP delta T.
Absolutely. That is the requirement of total rate of heat transfer. And you have a certain rate. So you can easily calculate how much length would be necessary. Because here, if you look at this value, the Q that is mentioned is 350 BTU per hour per feet. So MCP delta T divided by this parameter would give you the value of feet. Sahil Bairagi,
Yes, sir.
what is the length?
Just a second,
Can
sir.
you put? Yeah, sure.
Sir, I am getting 0.15 inches.
0.15
I
inch.
think I made a mistake in unit somewhere.
1.25 inch is the diameter of the pipe,
Yes, sir.
and you are getting 0.15 inch as the length.
Yes, sir. I should
Then
check
the
the
flow.
units again.
Yeah, check it.
Yes, sir.
But how are you calculating?
Sir, delta T m dot Cp by Qs.
Right. So here m dot is directly given, that 4 pound mass per second.
Yes, sir.
Cp is 1.
Yes, sir.
The delta T is 200 minus 55.
Yes, sir. And Q dot is 350 into 3.41 BTU per hour.
350 into
3.41 BTU per hour.
Q dot it's mentioned. I didn't get it. Q dot is what you are saying?
350 watt it is given. Now we have to convert it
No,
into
no,
BTU per hour.
No. I gave you. I corrected that in the next
Oh,
step. See,
oh,
I crossed that. 350 BTU
Oh,
per hour
okay,
per
okay.
feet.
Yes, sir, I got it.
So that surface temperature is 200.378 degree Fahrenheit.
Absolutely. Right. So it's slightly higher than the exit temperature. Slightly. I mean, it's almost reached its exponential plateau. If you remember the graph, that the temperature which was going of the exit temperature, it's increasing. Okay, so that has reached the value which is the kind of a mean flow temperature there, just near about. So 200 point something, absolutely fine. 200 point something Fahrenheit, obviously.
Sir, without knowing L, how did we understand whether we had to apply for fully developed or like for entry region, the Nusselt number?
Right. So that is why that is why in the first place you have to calculate L. It is not the sequence I asked you to calculate. I mean, I asked you to report the values.
Okay, sir. So if L was small, then we would have used the other format.
Yes. But here L would be how much? Around 6,000 feet,
Yes.
isn't it? So it's around 6,000 feet, and you have a diameter of that is 1.25 inch, and that you convert it to feet. Okay, multiplied by 10. It's negligible feet, even not say 1 feet or kind of value that is required in order to be considered as fully developed turbulent flow. And that is why you are safely applying Dittus-Boelter equation. It is the 10 times d that we consider in order to live for turbulent entry length in case of fully turbulent flow. Now, when we see that the Reynolds number is higher than 10,000, we consider it as a fully turbulent flow, because the transition zone or that range that we say, it's way lesser than that. So once we have it more than 10,000, we consider it as fully turbulent flow. Okay, so there are steps if you follow that it is fully not developed. Okay, so immediately we say that it is fully turbulent flow. When it is more than 10,000 in internal flow. And then we calculate the length of the pipe or the tube. The entrance length we leave as 10 times d, and we see that this 10 times d is very negligible value compared to the length that is required for this operation or that is being used. Once this is satisfied, we call then it is fully developed turbulent flow. Once this understood, we apply the Dittus-Boelter equation with appropriate n value. The exponent n value, whether it is cooling or heating. These are the simple steps you need to follow and have to remember. So the length, those who are calculating or have calculated, you see that it is in the magnitude of this value, in the order of this value. Clear? Any
Sir,
question? Yeah.
I did not get length as 6,000 feet. I mean,
How much? How much did you
Yes,
get?
sir. I got length as 1.6571 feet.
yes, sir.
Why? What is the value that you got for after MCP delta T?
Yes, that value of length is 1.6571 feet.
No, the Q dot, that is the MCP delta T, that or the M dot CP delta T.
Just a second.
580, I think.
Yes, that's 580.
580. Again,
Yes.
you are not mentioning about units. I am repeatedly asking you.
BTU per hour.
Be careful. That's where you are making mistake.
Oh, BTU per hour per LBM.
Look at the unit of M dot.
For 1 second.
What is M dot? Salman, leave your speaker on. I just wanted to hear. What is the unit of M dot?
Sir, unit of M dot is pound mass per second.
And you are mentioning that BTU per hour. Did you get the
Sir,
point?
when we multiply M dot with CP, the pound mass is getting cancelled because there is one pound mass in denominator of
Pound
CP.
must be, you were not getting my point. The value that you are reporting is BTU per second.
Okay,
And,
sir.
and you are dividing that with the BTU per hour.
Yes.
Nevertheless, did you get the point?
Yes, sir, I'm just following because like I always get confused in units. So like
So that is the
it's-
whole point. That is why we studied CPC at the first point. So that is why we should always write when we have this calculation. If you are confused, I would suggest that you write this kind of a say T minus whatever the T outlet minus T exit minus T inlet. And then while writing M dot, you write clearly this kind of parameter or this kind of notation. So here you have BTU, what I told you, BTU per pound mass per degree Fahrenheit multiplied by 155 degree Fahrenheit. So here pound mass cancels out, Fahrenheit cancels out. So I have 155 multiplied by 4. This much of BTU per second. But then you are dividing this with a constant surface heat flux, which is having a unit 350 BTU per hour feet. So either you convert this to BTU per second per feet, or you convert this to BTU per hour in the next step. That means multiply with 3600.
So now I'm getting that around 6,000.
Around 6,000. But now you got the point that if you had calculated this L value of the wrong in the first step, then the subsequent step would be wrong. the
Yes, sir.
calculation of Q dot as well as. Then how did you get the value of 2,200 when I asked you? I mean, you used 6,000 feet, right?
No, sir. There also I used 1.65. The answer I got earlier.
How,
It's
then
still,
how did you get the value?
that's what I'm checking right now. Calculation.
Okay. Remember, I corrected one of my value here already. I missed this hour parameters here in thermal conductivity value. So BTU per feet per degree Fahrenheit per hour. Any question? Soham, did you get the value?
No, sir, I'm checking again. Like,
Okay. And why did you make the mistake? I mean, you got some figures that is correct, right? The Reynolds number was correct. The Nusselt
so-
number was correct.
yes, sir. Initially, Reynolds number I calculated wrong, but that I corrected. Then finally, for L, I did not convert R to seconds, so that was wrong.
Okay. So again, this purposeful example has been shown here is because you are accustomed with the SI units and giving with a consistent pattern. But here you have something awkward that you have not seen earlier, possibly in detail or in several examples, the SPS unit. Although it is kind of absolute, I would say, but still sometimes people use it in a mixed manner. That is, they use feet, Fahrenheit, along with the say liter and all these kind of values. So we should be aware of these units. And when there is inconsistent unit, even a simple problem can give you a trouble.
Yes, sir.
So that is the first lesson in the CPC that we learned in the last semester. The dimensional homogeneity and consistency has to be checked during the process calculation. Every valid equation should be dimensionally homogeneous. Any governing equation that you write or that you will write in future has to be dimensionally homogeneous. And during the operation or the calculation, it has to be unit-wise consistent. Multiplication, division would not be any issue, but this addition and subtraction would create problem if there is inconsistent unit. Those who forgot that part, let me quickly tell you that the dimension, the units are the representation of dimension. So dimensionally homogeneous means I can write, say, U2 is equals to U1 plus GT with the conventional manner where U is meter per second. But then again here, if T is in minute or hour, the time, this equation is still valid because it is dimensionally homogeneous. But during calculation, you have to convert this minute to hour or second, whatever the value of meter or the velocity is mentioned. That is called the consistency in unit. So I stop here today. If you have any question, feel free to ask. Because now I want you to solve this internal forced convection. Let me tell you, classify a couple of problems. How would you find that in Incorpora and do it? So internal flow, go to the internal flow section or internal convection, forced convection. Internal forced convection, there would be laminar flow and turbulent flow. In both the cases, there will be two different types. One is constant surface temperature. The other one is the constant surface heat flux. So one category each problem you should identify and do it. Like we have done here for the turbulent and constant surface heat flux. So this thing we have done it here. What is left is the turbulent and constant surface temperature problem. When there is constant surface temperature, remember while calculating the surface, this kind of temperature or the temperature differences, you should always consider the concept of LMTD. For constant surface heat flux, that doesn't appear. Okay, so whenever there is a constant surface temperature problem, be aware and be careful that you have to use LMTD concept. The flow classification will help you to choose or opt for appropriate empirical relation to find out the value of Nusselt number, and so subsequently the value of convective heat transfer coefficient. So 4 problems you should again do from Incorpora Duet: laminar, constant surface temperature, constant heat flux; turbulent, constant surface temperature, constant heat flux problem. Then you should be thorough with the concept, I hope. If there is any issue, any problem, get back to me. Because in the next class or tomorrow morning, we will start the natural convection section. Okay, so we have a couple of 5 or 6 classes left. Our last class is on April 14th. So before that, I plan to cover natural convection and boiling and condensation, these 2 chapters.
Sir, and when will be the next test?
Forget about the test. At first, let's